Kaydı o başlamış ama kapatmış yani. Tamam. Umarım başlanır. Umarım başlar yani. Katılan olur umarım bu saatte de yani. Neyle ilgili telefonla da mı? Onunla da gir bari. Ben de telefonla girersem ama aynı şey mi diyeceğim. Bir de bakalım katılan kayıt başladığı için sonra da izleyebilirler. Ali Bey nasılsın? Ali Bey sen şeyi ne yapacaksın yeğenini? Pardon burada sesim açık. Nereye gitti onu alacağım bir yerden herhalde.
Çok kafayı gelecek şimdi hocam taksiyle. Arkadaşlarım hoşuma gitti. Maltepe'de Süreyya Maçı tarafında bir arkadaşım var.
Rahmetlikler var. 10 dakikada bir geliyor. Taksiye gerekme geldi.
Bence de düşüneceğim işte şu an.
Yani burada 1000 lira bir gel gel 2 orta 1000 lira.
Söyle. Hocam o da telefona katılsın da 2004 bir de sayısal olsun yani.
Yani bir şeye de toplayayım da bunlar da katılsınlar.
Seviye Hoca falan katılsın.
Evet.
Hocam söyleyin.
Benden çok yüklememi istiyor sanırım da yüklem. O yüzden giremiyorum. Toplantıya katılmıyorum. Yüklerim de bir şekilde bir gelirse benim çağrı gitmesin diye ben Instagram'da destek sana. Bir tane bir şey almış arkadaş zor bela şeyden girdim. Web sitesinden girdim. Bakmak için yaptım.
Öyle mi böyle? Onlar da katılabilir yani. Aman.
Benim balıklı alan. Yani. Baksanıza. İnanıyor musun? Gerçekleştirmek için. Engelini istiyor. Kolay biliyor musunuz? Ben derste onu anlatıyordum. Ne zaman alındı? Mayıs'ta verdi, Haziran'da verdi. Haziran 15, 18, ondan sonra
Kim hani bu kimse yok. Ravi Agarwal bağlanmadı. Bağlandı mı?
Dışarı çıktı hocam.
Çıktı mı? Sesi. Ha, tamam. Hello, Professor Ravi Agarwal.
Hi, how are you?
Fine, thanks. And you?
I'm okay.
I hope it's all right with Microsoft Teams.
Yeah, my daughter helped me.
That's good.
So how far you are from Istanbul?
How far from Istanbul? I couldn't understand. How
Yeah.
far?
Yes, your place.
9 minutes left to start with your talking.
Okay. I have been to 3-4 universities: Firad University, Technical University, University of Istanbul. So
Thank you for giving a plenary speaker. Thank you very much.
You're welcome. Can you see my picture? No.
I cannot see. You must share a camera
Oh.
button, and yeah.
But camera is on. Let me see. Open share.
Yeah.
Now,
And you can share your screen. On the right side top, on the top, there is a share button. Click on there. You will see that share screen.
let me call my daughter.
This is different. Microsoft Teams different.
Shiba. I know. But why my picture is not coming?
Your picture's not gonna come.
No. On this one. It should come.
I think we share your, we can see your screen is small.
There should be a light here.
I don't know, it's because your camera is turned the other way.
No. Camera is here.
I know, but there's another camera in the back, right? There's another camera in the back, you see?
Oh, so
Here.
I did some mistake.
There we go. That's it.
Okay, now you can see me.
Oh, we can see you. Nice to see you.
Yeah. Now I'll do it. Now it's okay. Yeah.
Can you see the slides, sir?
Yes. Existence and uniqueness results for a nonlinear integral equation related to infectious disease.
Yeah.
Infectious disease.
Perfect. Yes.
That's my field.
Perfect. That's good.
Okay.
Yeah, good.
Okay. अब दरवाजा बंद कर दिया.
I want to listen to this one.
No.
Infectious diseases. That's my
It
field.
is all mathematics.
Yes, but I know it's my field.
I have been to Turkey at least 15 times.
15 times. I
Yes.
hope next year's pandemic will finish, and we will be happy to invite you face to face here.
Yes, I will come. I like kofte.
That's good.
There is a near Blue Mosque.
Yeah.
There is a restaurant, a small restaurant.
Yeah. In Istanbul, there is a,
Sultana Kofte.
yeah.
That's. I have been to that place many times.
Yeah, I've seen in 1 or 2 times in Istanbul in conference, international conference. Several times, at least 2 times, I remember.
There was a conference just 15 days back, organized by Mustafa Bayram.
Mustafa Bayram, Yıldız Technical University, I think.
Yes. No, now he is in Firat University.
Yeah, the other university. Yeah, I remember what name of university. He changed the university
Right.
in last years, last 2 years time, I think.
Yes, yes.
I think we can, if we are ready, we can start with, or shall we write 2 minutes only left?
Yeah,
Start.
yeah, I'm ready.
Yeah. What about pandemic in your state, Texas?
Uh, uh, just now I saw the news. Our president got the virus. Biden, President Biden got the virus.
Mm.
So it is going on. Now they are not.
The same in Turkey as well. Pandemic goes on. New variants.
Yeah, yeah, yeah, yeah. I have been many times to Middle East University in Ankara.
In Ankara, Middle East University. That's yeah.
Middle East.
Technical University in
Yeah,
Ankara. One of the oldest universities and
yeah.
English teaching in English all courses.
Yes, yes. Actually, my many students are there. Then EG University.
One of the eminent universities.
EGG University. EGG.
EGG, yeah, that's one of the best universities in Turkey.
Yeah.
Oldest and research, as far as the research is considered, one of the in the top.
Yeah. Some of my students are there.
That's good. Your student, PhD students.
Not my PhD students. They came here with the to be talk to work with me.
Yeah,
Yeah, yeah. So almost 15 came
yeah,
over the period of 10 years. Almost 15 came.
yeah. I think now, dear participants, Professor Dr. Ravi P. Agarwal will give his talk. He is one of the very, very famous mathematician and applied mathematician, with more than 1,000 papers indexed by CG Expanded and CG. So we are honored to see him in our conference. Here you are, Professor Agarwal.
Thank you very much. So let me directly go to my lecture. Uh-oh. I'm not good in this. So
We are
I was sharing.
your talk, so the participant may follow, watch later on.
Can you see the can you see the slides?
Yes, we can see on the screen existence.
Okay, okay. So the title of my talk is Existence and Uniqueness Results for a Nonlinear Integral Equation Related to Infectious Disease. In the year 1976, there was a paper by Cook and Kaplan. The title was A Periodicity Threshold Theorem for Epidemics and Population Growth. What they did, they modeled this with the help of an integral equation xt as t minus tau to t f s x of s ds. This model was interpreted as a model for the spread of certain infectious diseases with periodic contact rate that varies seasonally. Here, xt represents the proportion of infectives in the population at time t. What they did, they assumed that the function f is periodic in t. The meaning of this one is that there is some w or omega, so that ft plus wx is same as ftx for all t in R. So is the proportion of new infectives per unit time, and tau here is the length of the time an individual remains infectious. What they did, they used Krasnoselski's fixed point theorem in a cone, and they got the existence, just the existence, not the uniqueness, of solutions for this integral equation. Now, in the year 1980, this was just 4 years later, Leggett and Williams, they wrote another paper. The title of the paper was A Fixed Point Theorem with Applications to an Infectious Diseases Model. So what they did, they generalized the Krasnoselski's fixed point theorem, and they used their theorem, and they got better results than Kaplan. Now, after this, there have been several generalizations. For example, in the year 1993, Nonlinear Analysis, there was a paper with the title Positive Almost Periodic Solutions. So instead of periodic solutions, they found almost periodic solutions. Then in the year 1997, there was another paper. This was also almost periodic solutions for some neutral nonlinear integral equations. Now, in the year 2007, we wrote a long paper. The title of our paper was Dynamics of Epidemics in Homogeneous Heterogeneous Populations and the Spreading of Multiple Interrelated Infectious Diseases, Constant Sign Periodic Solutions for the Discrete Model. So what we did in this paper, instead of considering the continuous model, we felt that discrete model is more appropriate. So instead of single equation, we considered the system of equations. Okay, and we considered over the entire set of numbers over this G. So in this one, what we did, some of these components may be negative. So what we did, we multiply ui by theta I, where theta I can be 1 or minus 1. That means some of the components in this one can be positive, some of the components can be negative. And then we were able to find the existence part of this type of problems. Now, in this work, we added several examples. Of course, we could not find the real-world examples, but constructing the examples is very, very difficult. But we were able to do it after several weeks. Then in the year 2000, we wrote another paper, Periodic Solutions of Nonlinear Integral Equations on Infinite Interval Modeling Infectious Diseases. So you see, Kaplan, he considered the case when the solution is periodic. We started considering the integral equation for the whole range of real numbers. So our integral equation was xt is equal to t minus tau to t kts f of s x of s ds. So we had here the kernel, and then the function. Now, what we did, we imposed some very general conditions on the functions k and f, and we were able to find the existence part with the help of some fixed point theorems, but we had to modify our function f so that the known fixed point theorems can be applied. Then there are several papers. One appeared in 2000, existence of positive pseudo-almost periodic solutions. Then there is a paper in 2011, existence of positive pseudo-almost periodic solutions. Then there is a paper in 2014, step methods for a system of integral equations from biomathematics. Then Journal of Function Spaces in 2020, global existence of solutions to a system of integral equations related to an epidemic model. Then there is a paper in 17, existence and uniqueness of positive periodic solutions for a class of integral equations with mixed monotone nonlinear terms. Another book which deals with this type of problems is by Lee, An Introduction to Mathematical Modeling of Infectious Diseases. Then there is another paper in Electronic Journal of Differential Equations and another paper in 2017. So things are going on, but I will, towards the end of my lecture, I will mention that several things are not yet done. So I'm going to discuss a paper which we published in 2021 in the journal Mathematics. The title was An Investigation of an Integral Equation Involving Convex, Concave Nonlinearities. So you need some sort of growth condition on the nonlinearity part. Okay. Without using the growth condition on the nonlinearity part, nothing works. You have to use some sort of condition. So what we did, we considered this equation xt as ft xt plus t minus tau to t ktsg s x of s ds over the whole real line. Once again, if you are looking only periodic solutions, then life is easy. But if you are considering the solutions over the whole real line, then it is not so easy. You need lots of background material. Okay. Now, what we need for this one, remember, I'm not going to assume the growth conditions. I'm going to assume that the function is convex or concave. Okay. So there is a, theorem which is actually a fixed point theorem for convex, concave, and non-decreasing operators, which is defined on the Banach space for a normal solid cone. So we will be able to provide sufficient conditions for the existence and uniqueness of positive solutions of this equation. That is what is the whole idea. Now, what is most important that we will be able to illustrate with the help of two examples, whatever results I have obtained in this paper. So first, let me start with the definition of a cone, which is well known, but just for the sake of completeness. So I assume that this is my Banach space, which is real. Zero vector is 0e, and then we define a cone if zeta u is in P for all zeta greater than 0, and u minus u is subset of P, and then u is 0e. Then we have to define the partial ordering, and it is defined as u less than or equal to PB if and only if B minus U is in P. Then we define a sector or interval UB, which is UB for all W in E, such that U less than or equal to P, W less than or equal to PB. That means in the partial ordering, it is an interval. I will be using this notation also. U less than PB. That means U minus P is in the interior of P. P0 denotes the interior of P. Okay. Then a cone P is said to be solid if interior is non-empty. A cone P is called normal if there exists a constant K such that UB in E, your U is less than or equal to E, but this is greater than 0, implies norm of U less than or equal to K norm of B. So this is called a normal cone. Then we define an operator which is operating F, which is a subset of E to E, is a given operator and P be a cone in E. Then A is non-decreasing with respect to the partial ordering. If UB belongs to F, U partial ordering B implies AU partial ordering AB. So this is non-decreasing definition. Now A is decreasing if the inequality is reversed. Then I define A is convex if F is convex set and for each eta between 0 and 1 and U and F in F, A eta U plus 1 minus eta B is in the partial ordering eta AU plus 1 minus eta AB. And we define A is concave in F. Just you reverse the inequality, then it is convex. Concave in F is a convex set. Okay. Now, in the year 2004, 2 Chinese and 1 Korean, Gu and Zhu is Chinese and Chao is Korean, they proved a theorem, and the title of their result was Partial Ordering Methods in Nonlinear Problems. This was in a proceeding of a conference. So I have written down this one as a lemma. Let P be a normal solid cone in E, and U0, B0 is in E. U0 in partial ordering, B0, that means interval. Let A be from this interval to E be an increasing operator. Suppose that one of the following conditions is satisfied. A is concave, AU0 greater in the partial ordering U0, and AB0 is less than or equal to B0. So either this condition holds or this condition holds. A is convex, AU0 is greater than or equal to U0, and AB0 less than or equal to B0. Then A admits one and only one fixed point. This is a very powerful result. We are assuming that the operator A is concave or convex, and the conditions for the interval at the end of the points of the interval or end of the what you call the elements. Okay, so then A admits one and only one fixed point. Moreover, there exists constants lambda positive and mu between 0 and 1, such that for all x0, that means you can start with any x0, the sequence defined by this xn plus 1 as axn converges to x star and satisfies this error bound. Now, let me just mention here, if you see this theorem carefully, you find that it is somewhat similar to what is known as the contraction mapping. But it is very different because in contraction mapping, you need that some sort of growth condition. Here, I'm not using growth condition. Here, what I'm using, A is either concave or A is convex. That is the basic difference here. Okay. Now here is my first theorem. Suppose that the following conditions are satisfied. So my function k is a nice function. It is continuous from R to R, and it maps to, that means it is positive. Then there exist two constants, m tau and capital M tau, such that the integral of this one for all t is greater than m tau, small m tau, but less than capital M tau. Okay, I will show you that each one of these conditions is needed. Number one. Number two, that each condition is reasonable. Okay, there exists a R between 0 and capital R, such that Fg is continuous. Now you see here, T is actually in whole of R, but X, the dependent variable, is between small r and capital R. Okay. For all t in R, the functions f and g R to R are concave and non-decreasing. So here is the condition, concave and non-decreasing. But you remember, I'm considering only in the sector. I'm not considering over the whole line. Okay. There exists alpha f, beta f, and alpha g, beta g. These are the constants, such that for all t in R, now you notice once again, here the condition is for all t, but with respect to the second, the dependent variable, it is at a small r. It is greater than or equal to alpha f r. Here I am replacing with capital R, less than or equal to beta f r. Similarly, G greater than alpha GR, and at the capital R, it is less than or equal to beta GR. And then I'm combining all these constants, which is my last condition. Alpha F plus alpha G MR is greater than 1, and beta F plus beta G M of R is less than or equal to 1. Okay. So you notice that this condition is entirely different from contraction mapping, where you need that the Lipschitz constant should be less than 1, strictly less than 1. But here, you will find that this plays the role of somewhat Lipschitz constant, but it is less than or equal to 1. Let us see the conclusion. Then, by the integral equation admits a unique continuous solution such that it lies between small r and capital R. What I'm trying to convince you that the solution which I'm getting with the help of this is already have the lower bound and capital bound, lower bound and the upper bound. That means small r and capital R play the bounds of lower bound and upper bound. What is most important here for computational purpose, that the solution has lower bound and upper bound, which you can use and you can improve your solution. Let us continue. Also, there exists a constant lambda positive and mu between 0 and 1, such that for any continuous function x0 satisfying between small r and capital R, the sequence defined by this converges uniformly to x star and satisfies this bound. That means it is a constructive result. It not only gives you existence, it gives you uniqueness, and it gives you a way how to actually construct the solution. Now, I'm not going to give you the complete proof. I'm just going to give you a few hints. You define E, you define norm, you define cone, and then you define the interior of the cone. This is all I need. And then you define U0 as small r, B0 as capital R, so that this becomes the sector. And then the first claim is that the operator maps the interval into E itself. Okay. Now for this one, I need to show that first that the operator A is continuous. So I need to go about the characteristic function and so on and so on. And I need dominant convergence theorem. And finally, I show that my operator is continuous. Then I need to show that the operator is bounded. Now here, the role of the monotonicity and convexity starts playing the role. So it turns out that my function ft(xt) is greater than alpha f u0, less than or equal to beta f b0, and the integral part is greater than alpha g u0 m0 and less than beta g b0 mr. Okay, so now you use these two and you will find that the operator I have defined, it is the lower bound is u0 alpha f plus alpha g mr, and the upper bound is b0 beta f plus bg mr. Now, next part, we need to show the operator is a non-decreasing operator with respect to partial order induced by f. So here I need the monotonicity property which I have assumed. But notice that it is for all t, but x and y are always in bisector. Okay, and then we need to show that A is a concave operator with respect to partial ordering. So here is the some hints how to show. It requires whatever we have assumed. And finally, we are able to show a u0t is greater than u0 and a b0t is less than b0. So all the requirements of the lemma which I have stated are satisfied, and the conclusion of theorem 1 follows. Okay. Now let me go to the second theorem. Second theorem remains almost the same. The only thing which I need here is slightly different, that the functions are, instead of concave, it is convex and non-decreasing. Otherwise, you will see that most of these conditions are almost the same. Only thing which is required, because I have two parts in my lemma. One part requires convex, one part requires concave. So concave I have assumed earlier, now I'm assuming convex. This condition remains almost just the reverse of this one, that this part is greater than part, this part is less than 1. Earlier it was greater than 1, strictly greater than 1. This was less than or equal to 1. So that role is changed. And then the conclusion remains the same, that there is a solution between small r and capital R, and the iterative scheme converges, and we can write down the error bound. So these are the two main results. I will say that the proof of the second result does not change much except few steps, and I will call that first result is the main result. Once you know the first result, you know the second result. Okay. Now the most difficult part in this one is construction of the examples. So this took several weeks to find meaningful examples. I'm going to consider this example. My integral equation is 2 1 plus e to the power minus t mod, because t can be with, negative to positive infinity. So I'm just putting here modulus sign, a square root of xt, 1 over 100 tau. Now, why I'm not putting here modulus sign? Because my x is always is positive. Okay, so from t minus tau, I have here 100 tau. Of course, you can construct now many examples, you can modify, you can get something better, but this was good enough to give an example. T minus tau to t e to the power minus t minus s square, and then this part. I have written down the result for this integral equation as a corollary. The integral equation 12 admits a unique continuous solution which lies between 1 and 100. Now, these numbers are not artificial. You will see that I will use these numbers. Of course, as I mentioned, that these numbers you can modify and but once again you have to work all the way again. Moreover, there exists constant lambda positive and mu between 0 and 1 such that for any continuous function x0 satisfying between 1 and here should be 100, the sequence xn defined by this one for all t converges uniformly, and this is the error bound. So I need to show that the requirements of theorem 1 are satisfied. Okay, so let us see. My FTU here is 1 plus e to the power minus t modulus square root u. Remember, t is in R and u is greater than or equal to 0. So this is well defined. KTS is e to the power minus t minus a whole square. So this is well defined. GTU is this nonlinear part which is well defined. So everything is well defined. So the requirement that my f should be continuous, k or g, whatever, everything is okay. My second requirement is that this should be, the integral of this one should be bounded. So certainly my KTS is greater than or equal to 0, so certainly lower bound can be 0. And then this part is same as e to the power minus t square whole square. This is always less than 1, so this is nothing but tau. So my small m tau is 0 and my capital M tau is tau. Okay. Now my small r is 1 and capital R is 100. So ft at 1 is greater than or equal to 2, and ft at 100, just little computation gives you less than 40, which is 3 over 5 times 100. Okay, and gt1 is greater than or equal to 0. gt100, little bit of computation gives you 2 over 5 tau less than 1 over 5 tau times 100. Okay, so my small r is 1, my capital R is 100, my alpha f is 2, my beta f is 3 over 5, alpha g is 0, beta g is 1 over 5 tau. So I have all the constants. Now what was the requirement? Alpha f plus alpha g m tau, which is nothing but alpha f, because alpha g is 0. So you get 2, which is greater than 1. That was the requirement. Then beta f plus beta g mg is 3 over 5 plus 1 over 5. This is same as 4 over 5, which is less than 1. So all the conditions of theorem 1 are satisfied. Therefore, the conclusion is holds. So let me just give you one more example. In this case, I am assuming f to be 0. So this is just a constant. This is t minus s whole square e to the power t minus whole square, and this is the part. Here, once again, my tau is greater than 0. Let me read the corollary. Here, I'm not able to find how small r is and how large capital R is. So here it is, for sufficiently small r positive and sufficiently large r, The integral equation 13 admits a unique continuous solution x star such that x star is more than r, less than r, capital R. Unfortunately, I'm not able to find small r and capital R, but sufficiently small r, and sufficiently large capital R. The conclusion is there exist constants lambda positive and mu between 0 and 1 such that for any continuous function satisfying between small r and capital R, the sequence defined by this converges uniformly to x star and satisfies this error bound. So let us see the details little bit. Here, as I said, my small f is 0. KTS is t minus h square e to the power minus t whole square. And GTU is 3 over 4 tau cube e to the power minus tau square, 2t square plus 1t square plus 1u plus u to the power minus u. So all the requirements about the function f, k, and g are satisfied. Now I need KTS. Remember, my KTS is here. This is more than 1, so KTS is greater than t minus square. And this is same as t minus h square e minus t square. Remember t minus s. What is t minus s? Let me go back. This is what is my integral. So my s is between t minus tau to t. Okay. That means this part is less than e to the power tau square. So this is what is the idea, that KTS is more than this and less than this. Now you can integrate. If you integrate, you find this is tau cube over 3, and this you find as tau cube over 3 e to the power tau square. So what you get? You get m tau is tau cube over 3 and capital MR as tau cube over 3 e to the power tau square. Okay. Now, the function g is convex and non-decreasing. There is no doubt about this one. Also, 1 plus e to the power minus r over r is greater than 4 e to the power tau square. Here it plays a sufficiently the condition that our small r is sufficiently small. So I assume that it is sufficiently small. So this is a very small quantity. This is greater than 1. So I can always assume this inequality. Okay. And finally, GTR is this part. Just little bit of computation shows that this is more than 3 over tau cube r. Now you choose r sufficiently large. Remember, that was my assumption. Small r is sufficiently small. Capital R is sufficiently large. What I need, that this is less than half. So GTR, I need to compute this at r. This is same as after some computation you get 9 over 4 tau cube e to the power minus tau square r. And so I get the constants alpha f, beta f is 0, alpha g is 3 over tau cube, beta g is 9 over 4 tau cube e to the power minus tau square. Compute these constants. It turns out to be exactly 1. It was greater than or equal to 1, so it is okay. This part should be less than 1. So you just substitute beta f, beta g, m of tau. You will find this is 3 over 4, which is less than 1. So all the conditions of theorem 2 are satisfied, and hence the conclusion holds. So this is the work which we did in 2021. Now let me go back. This was my equation. What is remaining? What happens when k is having some sort of discontinuity? Okay. That part is not yet done. Remember, my t is over whole of r. If it is periodic, then situation is very different. because then I don't have to deal with the whole real line. Then I have to deal only with the period. Whatever is the period. W was the period. So I need to consider only T over the period. Right? What happens if G is discontinuous with respect to S or with respect to X? What happens when function F is discontinuous with respect to the dependent variable? Okay. Now, considering directly the systems is not a problem. But considering when the function G, few components are increasing and few components are decreasing, or few components are convex and few components are concave. Okay. Now, one can argue about this one, what happens in the discrete case or what happens on the time scale. And nowadays there is a lot of interest on the fractional. So what happens on the fractional? All these questions are open, and I think someone will take it over and try to do something. Thank you very much for inviting me. If you have any question, I will be happy to answer.
Thank you very much for the interesting talk. Is there any questions online and face-to-face? No, thank you.
Okay. You have a nice day, and sorry, it should be evening. You should have a nice evening.
Thank you again.
Okay. Okay, so maybe next year situation will be better. Okay.
I hope next year will be face-to-face and after pandemic ends.
Yes, yes. Okay, okay, goodbye.
Goodbye.
Was there an excuse?